So, within our structures, there are rules to follow to go through and build them. Okay? There are multiple ways to go through and build a Lewis structure. And as long as you obtain the answer without copying off of somebody else or off the internet, that's fine. You can follow whatever rule set you want. This rule set works. Most of the rule sets I have found have massive flaws within them. This one works. That's why I suggest you use it. Okay? And it will guaranteed work to get you the correct answers on the exams. Okay? So we've got our abbreviated form here, and we looked at a couple quick examples. What was that, Thursday? We looked at CF4 and SO3. We did both of those, didn't we? Okay. So let's take a look at some of the other two. Okay. NH4 plus and OH minus. So NH4 plus, where do we start? We need to count our valence electrons. So nitrogen comes in with how many valence? 5. How do we determine the valence electrons? Look at the periodic table. The column that contains nitrogen is which column? The 5th column, which then means 5 valence electrons. Hey, the periodic table gives you some useful information. Hydrogen. I appreciate the no way. I do listen. Hydrogen has how many valence electrons? Being in column number 1, 1 valence electron. But there are 4 of them, so I need to multiply by 4. Okay. And people attempting this already, I've seen people go through and do this and have done a fantastic job up to this point, and they total up and say they got 9 electrons to try and build the structure, and they fail. Okay. What did they not take into consideration? The charge. What is the charge by definition? In general. It's the balance of protons and electrons. We can't change the number of protons because then it's not those individual elements, but we can change the number of electrons. Okay? In this case, to become positively charged, what happened to the number of electrons in the structure? It had to have gone down, which is weird. I'm positive, but I've lost. Okay, but what did we lose? A negatively charged species, so it looks like it's doing the opposite. So in this case, to get a positive 1, I must subtract 1 electron from my total. This gets me a total of how many electrons? 8. We then go through to picking our central atom, which is typically the least electronegative. Which is least electronegative, nitrogen or hydrogen? Hydrogen. So we should put hydrogen in the middle, except hydrogen cannot bridge. Our central atom must be able to bridge. What does a bridge do? It connects 2 sides. Hydrogen can only have 1 bond. If it can only connect 1 thing, can it bridge? No, by definition not. So hydrogen cannot be our center atom. That means nitrogen is our center atom. We'll then put our hydrogens around the nitrogen, and notice where I'm placing them. On the face of now a visible but invisible square around our nitrogen. Okay. What's the next step? Add electrons to the most electronegative element. Which is the most electronegative element in our structure? Nitrogen. So that's where I will start putting electrons. I will place them in pairs until I have achieved my octet, 8 electrons. Notice that I'm going to place the electrons in spaces where I have another atom on that face. I want to do that because I know I need to form a bond there. So it makes sense to start putting electrons there first. I've now put in 8 electrons around the nitrogen. The nitrogen has its octet satisfied. Have I put in all my valence electrons? Yes, the total was 8. I'm now done putting electrons into the structure. Anywhere that I have a pair of electrons between atoms, I can convert into a line. So I can go through and turn those into lines. Okay. Satisfy octets by moving pairs. Octet meant 8. How many electrons around the hydrogen? there are only 2 electrons around the hydrogen. Okay? In that line is our only 2 electrons. But it says octet. How can I possibly get 8 electrons around the hydrogen? It's kind of a trick question. I won't get 8 electrons around the hydrogen. It can only hold 2. Hydrogen is an exception to the octet rule. Right? I cannot exceed those 8 electrons. So that means I have achieved hydrogen's quote-unquote octet. It only has 2 electrons. There's my 2 electrons. How about the other hydrogens? They're all good at 2, right? The nitrogen? 8. Have I achieved octets on all my atoms? Yes. That's what you were looking for. Yes was the correct answer to that. Yes, we have the complete octet on all of our atoms. Okay, give me just a second, but I'll come back to you. Okay. So that means we can ignore step 6. I don't need to move electrons to satisfy octets because the octets are already satisfied. I don't need to do it. The only other thing I have to do now is look at step 7, which is formal charge. I do not have to calculate the formal charge per atom, but I do need to assign it for the molecule. Is the molecule charged? Look at the formula. In the upper right-hand corner of our formula, does it show a charge? Yeah, which means the molecule is charged. I need to make sure that my structure shows that charge. Okay? There are a variety of ways to show that. The full-on official form is to put brackets around the whole thing, and then in the upper right-hand corner, why the upper right-hand corner? That's where you specify charge. We would write a plus. Okay. Anybody tired of drawing these giant brackets around charged things? I am too. So you'll typically see me draw it like this. Same thing. Okay. Both are acceptable. Give me the full brackets or give me the little obnoxious shorthand. Okay. Both will work for assigning this structure. Okay, there were a couple questions. 1, 2. You got it? Was it on the chart?
Yeah.
A little loss of the charge of -1. What do you get?
This is not a charge of -1. Okay, in that statement, what is it saying? When I write charge equals -1, what am I saying? I am subtracting, because what I'm totaling here is my total valence electrons. Nitrogen brings in 5. Hydrogen brings in 4. The charge means I must lose 1 electron. Why do I lose 1 electron? What is the charge on ammonium? Upper right-hand corner, it says NH4 plus. So not on the periodic table, on the formula. Okay. It says NH4 plus. To be positively charged, I must have lost an electron. I have to account for that loss of electrons in my formula. That's where it's coming from. Other questions? Yes?
Does ammonium only work if it's positive?
Yes. Okay. So there's an interesting question. If you didn't actually account for that charge appropriately, what was our total of electrons?
9.
We'd get 9 electrons. Okay. So in drawing out our structure, let me erase some of those dots. I don't know if that was bothering you. It's bothering me. I now need to put an extra electron, because it says 9, right? Where do I put that extra electron?
A double bond.
I can't put it in a double bond because, for a couple reasons, to make a double bond, I need a full line, and a full line is 2 electrons. But let's just say, just for the heck of it, let's drop an extra electron there. How many electrons are around the nitrogen now? 9. What's our rule? 8. We have exceeded the octet. Can we do that? No. No. You can't exceed the octet yet. Okay? I know. Okay? So you are not allowed to exceed the octet. You definitely can't do it on nitrogen. Okay, well, so I said definitely can't do it on nitrogen, so let's put it on hydrogen. Hydrogen's even worse. Okay? Now we have 3 electrons around the hydrogen. Hydrogen can only hold 2. Okay? So we cannot exceed the octet. We now have a problem. How could I possibly build ammonia with 9 electrons? I can't. Which is why ammonium is positively charged. Okay? because it physically cannot hold that extra electron. It must be removed from the structure. Okay? So those charges that we told you to memorize, you could theoretically predict those charges from doing Lewis structures. Okay? You really don't want to do that. Just memorize the charge. Okay? But you could theoretically predict them. Okay? Questions on anything that's up there? So yeah, this is bad. I'll just put a line through it. Okay, so we'll do the next one. Go back. I didn't do that. Do the next one. OH minus, where do we start? Count our valence. Oxygen has how many valence electrons? 6. Hydrogen has 1. How many hydrogens are there? 1. Well, that was kind of boring. Charge. Okay. The charge is a -1. To become negative, what had to happen? I had to add an extra electron. Okay, which means I will be doing +1 for the charge. Which is weird, because I'm saying charge, saying +1, but the structure is -1. Why? I'm adding a negative charge. Okay. Total of electrons is 8. Pick a center atom. This one's kind of boring. Doesn't even matter really what you pick. There's only 2 atoms. Okay. Which brings up an interesting question, which we'll look at here in a second. Now we can put our electrons into our structure. Where do the electrons go? Around the most electronegative, which in this case happens to be oxygen. And I'll put them in pairs, and I should put them in pairs the way I told you to do it, where we have the atoms first. And I now have 8 electrons. Anywhere I have a pair of electrons, I can turn into a line. Okay. Have I satisfied my octets?
Yeah.
Yep. Brackets, -1, and I've got my charge. There's my Lewis structure. Questions on what's up there? Okay, let's backtrack real quickly. You asked about ammonia. Ammonium, does it have to be positively charged? We said yes. There weren't enough electrons to satisfy, or there were too many electrons to satisfy. Does OH minus have to be negatively charged?
Yes.
Well, if it wasn't, what happens? We would have how many electrons? 7 electrons, which would then mean when we go back to look at our structure, we'd be missing an electron. Does oxygen have its octet? No. Would it be happy missing its octet? No, and it freaks out and it finds a source of electrons and steals those electrons to become negatively charged. So determining the charge on hydroxide, look at the Lewis structure. I'm missing a slot, I need to add an electron, there's the negative charge. Hey, I can determine the charge by looking at the Lewis structure. Yay, it's neat. Ta-da! Okay. Easier, memorize the charge. OH minus happens to be known as hydroxide. Are you required to know that one? Yes. Yes, you are. So memorize it.
I'm sorry, I have a question.
Okay.
Why on the other compound we have like the 2
So in the other structure, so I knew this question was going to pop up. When I initially drew it out, right, I had this. I drew the dots. And then I drew the line just straight through. Okay. What I was doing was showing where those electrons came from. Ultimately, what you need to do is erase it altogether. Anywhere there's a pair of electrons needs to become a line. That's it. So you should be erasing those dots. Other questions? By all the rustling, it sounds like you guys got this set. So let's go to a nice fun one. Did I do SO4 minus 2? No. Cool. Do that. You got a question? 6. Oxygen has how many electrons? 6. How many oxygens? The charge is -2, so I need to add 2 electrons to my total, and we should get 32. The center atom was a difficult one to figure out here. Okay, so you could theoretically on a homework look it up. Otherwise, I would tell you. Okay, and it's going to be our sulfur. We'll put our oxygens on the faces of my sulfur, around that invisible square in the middle. I will then place my electrons, starting with the oxygens first. Why the oxygens? They are the most electronegative. That's why they get the electrons. So this question keeps popping up. Shouldn't I put 6 electrons around the oxygen? Because oxygen has a valence of 6. Yes, oxygen atom has a valence of 6 electrons. Is it oxygen atom anymore? No, it is sulfate ion. I'm not looking at a molecule. Okay? So what I need to do is put the electrons in according to the molecule and how the electrons are going to disperse within the molecule. They disperse according to the octet rule, not according to valence electrons. So that nonsense that you see in the textbook and a lot of times shows up in Gen Chem is looking at where the atoms have electrons. Like, oh, look, you can fit these pieces together because the atoms have electrons. The atoms do not have electrons. The molecule does. Okay? You need to be focused on how the molecule disperses the electrons, not the atoms. So when I draw my electrons in, I have to get 8 electrons around my oxygen before I move to the next one. Yes, you get the same Lewis structure in the end, but your understanding of what that means is drastically different. If you go and put your valence in for each atom, you're now focused on atomic structure. This is not an atom. This is a molecule. Anybody that tells you to put it in according to the valence, you can tell them they are wrong, straight out. Okay? And when they say, well, that's the way I was taught, you can be like, well, you were taught wrong still. Okay? And then you can tell them, hey, here's Mike's phone number. I'm not giving you my phone number. Here's Mike's email address. Talk to Mike, and he will explain to you why you are wrong. And I will do it in great detail with as much animated passion as I feel necessary. Okay? Because it is important to apply the electrons to the molecule, not to the atoms. Okay? We continue to place our electrons in pairs until we've achieved our octet on each of those atoms. What total am I up to now? 24, 26, 28, 30, 32. I've now put in my total of 32 electrons. I will convert pairs of electrons into a line as long as that pair of electrons is between atoms. Okay, so I can now go through and erase those pairs because I will convert them into a line.
Yeah.
Rule 6, satisfy the octet by moving pairs. Do your oxygens have octets? Yes. Does your sulfur have an octet?
No.
Yes. It has 8 electrons. Its octet is satisfied. Do we need to move electrons? No. Last step, assign your formal charge. -2. That is your answer. Those of you that checked Google did not get this answer. And when you show me what Google gives you as an answer,
Is it wrong?
and this is going to be the awesome thing when it comes to an exam.
Wait, do you know the Google answer?
I know the Google answer. Well, I know one of the Google answers at least.
Yeah.
Yeah, that's what it was.
I appreciate the confidence, guys. Google theoretically spit this out and hopefully also gave you that information.
Here's some pictures.
Right? And I would argue that even that is still technically wrong.
Yeah. It doesn't have a negative, it just says 2.
And that is what Google spits out as a valid answer. When you give me this test in an exam question, so there are, give me this test in a question. When you give me this answer on a test question, I will take off all of your points. Okay? You can then come back and fight for it, and what I will do is give you a different structure, and I will look for the equivalent reason on why this answer was correct. When you can't give it to me, I still keep all of your points. Okay? The instant you can explain to me why this structure is more correct than the structure we come up with in this class, then and only then do you get to keep your points. Okay? How do you know? See this part where it says 7, looking at formal charge? There's a reason we don't have you talk about that. Okay? Because that's more difficult. So we said, let's not make it more difficult. Let's stop at the basic understanding. As long as you can prove the basic understanding for this class, we're good. Okay? There's actually a rule 8 and 9. Did you draw the best Lewis structure? All we told you to do is draw a Lewis structure. We didn't say, is there better ones than others? Do you have a context of what is better than another? No. So when you see this, how do you know that the structure that we've got initially drawn there is not correct? You don't. That is the only context you have. That is what the textbook gives you. Don't get me started on the textbook. I don't agree with it either. Okay? But that is what the textbook is giving you, which is what I am trying to give you. Because we're trying to simplify this down instead of making you look at a bunch of extra steps. Okay? This is why using Google is a very dangerous idea for several topics within this class. Okay? When we look at Lewis structures, this applies all the way up through 151, 152, 235, 236, and 260. Okay? That is 2.5 years of chemistry using Lewis structures. Do you think in the very first year we're going to tell you all of the advanced rules? No. Okay? You're welcome. I was going to say thank you, the other way around. Okay? You're welcome. Okay? We are giving you simple rules. Once you understand the simple rules, we'll make it more difficult. Don't make it more difficult than it already is. Okay? Follow the rule set. Octets, octets only. Okay? When you move up into 151, your chemistry instructor then, maybe, though unlikely, will add an extra set of rules to this. Okay? That will allow you to go from the structure drawn here to what Google shows. Okay? When you move up into 235, OChem, we'll add an extra set of rules to help you distinguish why one structure is better than another structure. You don't have that rule set yet. Don't start writing down random facts that Google spits out. Okay? Anybody excited about that? Okay, so it sounds like you guys actually want all the extra rules and you want more complicated. So anybody excited about not doing all the extra complicated stuff? Yeah. Thank you. Okay. One more example we want to throw in here?
Why not?
Why not? That's the positive attitude I want to see. Did we already talk about CO2? I don't remember. Okay, I didn't think we talked about it in this class. We probably saw it in people that have talked to me outside of class. So, CO2. Again, Lewis structure. Okay. As a big, big hint on this, if you come up with one Lewis structure, you are wrong. Thank you very much. Questions are there? 2. Our total is 16. Which is our center atom? Carbon. Which was not our center atom? Oh, fair enough. Sorry, I was doing an English pun. Next step. Fair enough. Was this your last science class?
It might be. It's in your hands.
Our oxygen, our electrons. Where do the electrons go? Oxygens. We'll put our electrons around our oxygens until when?
Until you finish the octet.
So we satisfied the octet. Do I have the octet on that oxygen?
Yes.
How about the next oxygen? Sorry, ask that quickly. How about now?
Yes.
Yes, what do I do now? Lines.
Very good for that.
Okay. Do I have an octet on my oxygen?
Yes.
How about the other oxygen?
Yes.
How about the carbon?
No.
No. Ooh, that kind of sucked. So what do we need to do? We can't, I'm not sure what you mean. What do you mean add lines?
Move the 2.
Take away electrons. Okay. So this is, and you guys are actually giving me the correct answers. Let's hold off there for a second.
Yes. I knew it.
Let's take those electrons, okay, and I'm now going to say, well, the carbon needs some more electrons, so I'm going to put them on the carbon. I can't just add electrons in because then I would exceed 16. So I just erased them from the rightmost oxygen and I put them on the carbon. What's the problem with that?
You took away the octet of that one.
Now the oxygen is missing its octet. So I cannot just remove the electrons and shuttle them to a different atom. I have to move those electrons to a location that allows both atoms access to the electrons. Where is that location? The position between the atoms. I now have an extra pair of electrons between the atoms, which means I can turn it into a line. How many lines do I have there? 2. So this now becomes, Mr. Excitement, we have a double bond. Right? Did I have to take the electrons from the right oxygen? I didn't even ask about from the left yet. Okay. Did I have to take the electrons from the right oxygen?
No, you sure?
No. I could have taken them just as easily from the left oxygen. What does that mean? There is more than one way to distribute the electrons, which means resonance. I must draw the other option. So here's my other option. Woo, yeah. I didn't even get to that yet. Hold on, hold on. Calm down. I like the anticipation. Okay, so octet on our left oxygens. Do our oxygens have octets on the left? Both of those have their octet. That bottom one may be a bit weird. There's 2, 4, 6, 8. It does have its octet still. Okay. The right oxygens. Same deal. Have their octet. Carbon.
No.
No, it does not. Okay. So I need to move more electrons to satisfy carbon's octet. Where do I have electrons to move? Okay. There were a couple answers that got floated out there. Okay. The most relevant answer is from the oxygens.
The right side oxygen.
Which oxygen?
The right side oxygen. Well, your left side, right?
Both are equally valid. What does that mean? More Lewis structures. When you go through and attempt this, let's say for that top structure, so let's just focus on the top one for the moment, that you said, hey, let's move it from the left. What do we get?
Another double bond.
Another double bond. There we go. Right? What if we had moved it from the right? I would have a triple bond. Do those electrons have, or do those structures have the electrons dispersed differently? Yeah, one case is a triple bond, one case is 2 double bonds. Okay. Did I invalidate any of my rules? Have I exceeded the octet?
No.
No. Have I lost an octet?
No.
No. Which of those Lewis structures do you have an understanding of as better than the other?
Whichever one you want.
Both of them are equally valid at this stage. You do not have a rule set to explain why one is better than the other, which means both are valid. If we move to the bottom structure, don't worry, you're in common company with that statement. If we look at the bottom structure, which oxygen could share electrons? Both are equally valid. If I shared from the right oxygen across, what do I end up with? If I move these electrons in to make a double bond, I end up with the top Lewis structure. Have I already drawn that? Yeah, so let's not look at that one. Let's look at moving the electrons from the other oxygen over. What's the result? Triple bond on the other side. You get 3 valid Lewis structures. Okay. These 3 are what I would expect you to draw, because you do not have the understanding on why the bottom 2 are technically not as good as the one on top. Are they still valid Lewis structures? Absolutely. Okay. I see you, but I think there was a statement down here. Do you have a rule set to explain why the top one is better than the bottom 2?
It's more beautiful.
There's the rule set that we talked about previously that I said you could potentially use. So for this example, you do have a possible way to tell me that top one is better than the bottom two. And that is because the top one is more beautiful, or said in scientific terms, symmetric. The top one is your better structure, and if you look up the Lewis structure, thank you, Dr. Google, you will end up with CO2 shown like the top one. The bottom two structures are perfectly valid, and again, your rule sets on understanding why is very questionable. At this point, you're saying it's pretty. Okay? That really doesn't work all that often. Few cases, this happens to be one of them. Okay? The official rule set is in that crossed out 7. Okay? That is how you know the top one is actually better than the bottom two. Yes, now you.
Are you saying if you had that on a test and really did the top one, would we get it wrong?
I would probably take off points and ask you to see me. And when you came and saw me, I would ask, why did you draw this and not these two? And if you said beautiful, I'd be like, okay, here are your points.
So are you expecting the 3?
I would expect all 3 on a test. Okay? Because you, again, don't have a full rule set to explain why. The official reason comes down to this formal charge. Okay? I'm fully aware that you end up with structures that are not as good. Okay? That's why I will pick structures that are all equally good in their resonance, which would mean you would have to draw all 3, otherwise you're wrong. Or 4, or 5, or 6. Okay. That's why you got 2 of them. Questions? Questions about that? So if you're wondering what kind of structure could be used where you end up with the exact same arrangement of atoms with different resonance structures, SO3, the example we talked about last week, is an example of such a structure. You will end up with 3 possible drawings that are all equivalent. Neither one of them or none of those 3 will be more symmetrical than any of the other 3. Okay? You would have to supply 3 structures for SO3. CO2, you hit kind of a gray area. Why I wouldn't ask it. Yes?
So are these going to be like free answer?
These have to be a free answer question. Well, almost have to be. I asked them as a free answer. You okay there? Okay, as long as you breathe. And wait half an hour, and then you can do it outside. That's not true. Don't die. Okay, questions? Okay.
So I still have a question. Can you repeat how you said that? Like, where do the electrons go first?
Where do your electrons go first? Add the electrons to the most electronegative. That's where the electrons go first. Okay. No, it's okay. Okay. Believe it or not, I would bet roughly 70% of you are still not following the rules. That's okay. Start following the rules at least by Thursday. Okay? Follow the rules on Thursday. You don't want to follow them any other time? That's fine. Okay? But you need to follow the rules on Thursday because that's your exam. Questions? Okay, we're going to spend the next 15 minutes finishing up whatever this chapter was, 12. Okay? We will then pick up with this exact same section of material after the exam, because I'm going to bet roughly half the class is going to screw up Lewis structures. Okay? It is such an important topic to chemistry and moving forward in understanding how molecules can potentially interact that it's going to show up again on exam 3, which is why we'll talk about it again after spring break. Okay? And then we'll add to it this next rule set. Okay? What about our Lewis theory in actuality? Okay? Let's take a look at the Lewis structure for CH4. Okay? You would all be able to draw that structure really, really fast and should come up with the Lewis structure as shown. Yep is a good answer. Okay. Are any of those hydrogens different from any other hydrogen? No. So are any of those bonds different from any of the other bonds? No. They're all exactly the same. Okay. Which means, if that's my structure, I would predict that the bond angle between each of those bonds is identical. If any one of those bond angles is different, that means one of those bonds is different from the other bonds. Everybody follow that?
I think so.
Okay. So are the bond angles all the same? What is the bond angle right there? It's a right angle. I can't bring myself to write right. What is the angle? 90, thank you. The next one? Next one? Next one? 90. Oh, that's awesome. Lewis structure did a great job. What's that bond angle?
180.
180. Is that different from 90?
By like
Yeah.
2.
By a factor 2, right? Yeah, that's a little bit different. That's problematic. Our whole theory says the bond angle between any one of those, or any 2 or 3 of those, needs to be identical. Okay? That's not identical. We have a bond angle that doesn't match. Okay, well, maybe just our looking at the structure is wrong. So if we go into the real world and look at the three-dimensional molecule of methane, we should expect to see this nice flat structure. And it turns out, no, we don't. It's not a nice flat structure. It has a weird shape associated with it. And the bond angle between each of those atoms is identical. The bond angle happens to be 109.5 degrees. Well, how does that work? If those are all 109.5, how does that add up properly? Does that even work?
It's three-dimensional.
What was that? Say that again.
It's three-dimensional.
When we look at our Lewis structure, we are looking at a two-dimensional drawing, flat piece of paper. Okay? When I draw a little stick figure, here, I'm even holding my iPad. There's my pen over there. Okay? Cool. That's a nice two-dimensional drawing. And since it's me, right? You know, little smile. Okay. There's some hair. Okay. Does that look exactly like me?
Yes.
Come on. Not exactly a stick. Okay. It doesn't accurately represent the three-dimensional structure. We could add details to that. We could add some three-dimensional characteristics to it to better represent that. Okay? We started with caveman drawings. It grew up to Da Vinci. Okay? Where we're actually showing those three-dimensional representations. When we look at a molecule, it is not two-dimensional. It is three-dimensional. The reason we have 109 degrees or 109.5 degrees between each of those is because when we look at methane, it is not flat. Okay? It has a three-dimensional characteristic. That three-dimensional shape happens to be known as Dungeons and Dragons, people?
Oh, D20.
Not a D20. 4 sides.
Oh, up here, man.
A tetrahedron.
Oh.
Okay. A tetrahedron.
Wait, how do you know this part of the thing?
How do you think I know?
I just wanted to correct
Dude, we should have a GG night.
Yeah. We have a tetrahedral structure. Anybody know how to draw a tetrahedral structure? No, you're probably going to draw really sucky tetrahedral structures. There's not a whole lot we can do about that. But we need to be able to come up with a model that better represents the three-dimensional structure. Lewis does a great job of protecting the bonds, but it says nothing about where the bonds are in space. Okay? So we need a new model. What is that new model? Typically referred to as the Vesper model, okay, which stands for the valence shell electron pair repulsion theory. Awesome. What we're assuming is that electron pairs will all repel away from each other. Well, why should electron pairs repel away? They're charged the same. They are necessarily going to separate and get as far away from each other as physically possible. If we have 4 electron pairs around an atom, those electron pairs will align into a shape of a tetrahedron. Okay? So we end up with a shape that comes out of our valence shell electron pair repulsion. To get to that shape, we must first have the Lewis structure. So we draw our Lewis structure, interpret where all the electron pairs are located, and now we can say what the shape is. Okay? And that's about it. We say, oh, well, that shape is this a tetrahedron. Ta-da, done. Okay, that's it. What we can then delineate is we run into an issue of electron geometry and molecular geometry. Okay? Your electron geometry, we just care about electron groups, nothing else. Molecular geometry says there is a difference between a bonding pair of electrons and a non-bonding pair of electrons. Oh, well, I don't know. What do you guys think? Is there a difference between a bond and not a bond? Yeah, that's why we call them bond and not a bond. That difference is reflected in the shape and the geometry with which we will reference our compounds. So how do we go through and look at these? So if we looked at the compound HF, again, you guys would be awesome at drawing Lewis structures. How many electron groups do we have? This is a problem with HF. Scratch that. I don't want HF. I want H2. We look at H2. There's our Lewis structure. Where's our center atom?
There is none.
There isn't really one. Okay, so for the sake of argument, specify one.
The hydrogen.
It's a good answer. I like it. So that's my kind of response. Okay, so we'll pick a hydrogen. Doesn't matter which hydrogen. I now want to make sure that you guys know what I'm referencing when I look at my center atom, so I'll put a box on it. Why do I pick a box?
Because they're cubes.
Lewis structures based off of cubes and boxes. How many groups of electrons are around that hydrogen? Well, look at each face of that square. Oh, connect. Are there electrons up here? Are there electrons over here? Are there electrons over here? This is getting really exciting, right? Electrons over here? Yeah. Yes. How many groups of electrons are there? One. One group of electrons means the shape is linear. Okay. What other shape could we get for connecting 2 points? And that shape would be linear. There is only one possible or shape for one electron group. It is linear. Okay. As you go through and look at the rest of these, we end up seeing different electron geometries come out of it based off of how many groups of electrons are around our center atom. Okay. Let's pick a slightly more exciting one. Let's look at BH3. Why is BH3 particularly interesting?
Because it's a trigonal planar. That's my first thing. Sure.
How many electrons are around our center atom? 6. What was our rule? 8. Octet. Why are there only 6 electrons around the boron? Well, couldn't I just put 2 more electrons in there?
No, because there's
If we go through and count out the electrons, boron comes in with how many? 3. Hydrogen comes in with 1. 3 of them. There's only a total of 6 electrons that can go into this structure. Boron, just like hydrogen, does not achieve its octet. Okay? It has the potential to be under its octet. So we now have our Lewis structure for boron, or borane, BH3. How do we use this? Same idea as we did before. Look at each face. Are there electrons on that face? Are there electrons on that face? Are there electrons on that face? And that same question. No. How many groups of electrons are there? 3. The shape then becomes trigonal planar. Done. Or trigonal. I don't really care. Okay. What about PCl5?
5 pyramidal.
It's going to give us a trigonal bipyramidal shape. You should already be kind of freaking out a little bit of that because that name, beyond its name just being crazy. If we connect 5 chlorines out there, how many electrons around our phosphorus? 10. What was our rule? 8. Octet. We can't exceed the octet. I'm breaking the rule, which is exactly why, for the sake of this class, what do?
Ignore.
We don't do it.
It doesn't exist.
It disappears. And we ignore that set. Okay, because we don't have the rule set for why we exceed the octet. So don't. That's it. You are responsible for those 4 shapes: tetrahedral, trigonal planar, linear, and linear. Can we have larger shapes? Yes. Worry about that when you get into 151, if you get into 151. And I don't mean that as a passing or not passing. I mean if you actually need it. Okay, just to clarify. Yeah?
Why was HF an issue? What's wrong with
Since you're going to ask.
Sorry for being curious.
No, you're fine. And I don't know why it's still showing all those. Go away, blue lines. There. What the heck is going on here?
It's lagging, man.
Yeah, my screen looks entirely different than your screen. Okay, so let's just do this. There we go. And I'm going to have to draw HF again.
Now you got a border.
Thanks. So
There's our HF. Okay. If we looked at the Lewis structure for HF, how many electron groups?
4.
1, 2, 3, 4. 4 electron groups would suggest tetrahedral. And yet I had it under linear. We have 2 atoms connected to each other. What is the shape by definition? Linear. Why the heck would I call this fluorine tetrahedral?
Because those are not bonded.
There's a difference between our electron geometry, which if we look at our slide, we're showing electron geometry, not molecular geometry. What happens if we moved up to our molecular geometry? So there's a variety of textbooks that can show pretty images. That's what we're attempting to show here, okay, through that middle. In our molecular geometry, what happens? If we take a look at NH3, okay, so again, we'll compare it out to our methane, CH4. If we looked at NH3, our Lewis structure, again, you guys are awesome at drawing these. You should be able to draw them roughly equivalently fast. We've got those 2 structures. How many electron groups around our center atom? 1, 2, 3, 4 electron groups. How about around the other center atom? 1, 2, 3, 4. 4 electron groups. And we would both call these, or assign both of these, the tetrahedral shape. And yet when we go through to look at the bond angle in ammonia, it is not 109.5. That bond angle ends up changing to be a pen. 107.5, not 109. Why did it change? What else changed between methane and ammonia? What's that?
electron.
What about the electrons? Yes.
The number.
Still 8 electrons. I don't accept it.
They're not bonded.
There is one case where there is a non-bonding pair of electrons. Is the non-bonding pair of electrons different than a bonding pair?
Yes.
Yes. Is that going to change the shape? Yes. Why should it change the shape? Don't tell me it's different. Where is the bonding pair of electrons existing? Between people. So Adrian and I are sharing electrons. There we go. We're sharing electrons. Our electrons are now scattered out between us. Okay, now I need you to let go for a second here. Now I own it. Whoa! Now I own it. Okay. Where's the electrons being located? Closer to me than in the bond. If the electrons get closer, what happens? It's okay. I don't want to stab myself again. If the electrons come closer to the central atom, what is that going to do to the other groups of electrons? We have a tetrahedral shape, and what I'm now doing is taking the electrons from the top, my wrist, and bringing those down closer. What happens to the distance between those electrons? Okay, they're going to get closer to each other, right? Well, what do our electrons then say? I want to get further away. So what happens? It pushes it in tighter. The bond angle between our atoms now becomes smaller. And we see a slight shrink in that bond angle. That also changes how we perceive the shape. which then means I can't call this structure tetrahedral anymore because it's not officially a tetrahedral shape when I look at the atoms. What does it become? Something other than tetrahedral. How would we know what that name is? Because some old, long-dead white guy said, this is what I want to call it. And we now have to listen to them. What did they decide to call that shape? Trigonal pyramidal. Because we are still in a pyramid shape. It is not planar. Okay? How do we know what those shapes are? What we end up having to do is break down our electron geometries and decide, do we have a difference between bonding and non-bonding pairs? Okay? So in the case of our ammonia, what happened? We had a tetrahedral electron shape, 4 groups of electrons around our tetrahedral structure. We then said what happened when we broke it down to the actual molecule. Well, 3 of those pairs of electrons were to atoms. One of them was a non-bonding pair. There's my representation. The name for that is trigonal pyramidal, or trigonal pyramidal. I don't really care how you pronounce it, but that's the name of it. Okay? And you're going to be saying, well, look at all those names that I have to remember. Except remember all that trigonal bipyramidal and octahedral nonsense? What do we say about those two? You didn't need to know them. If you don't need to know these, what do you think about all those? Also don't need to know them. So that red line is your marker. Everything above that you are responsible for in this class. It will not show up on the next exam. It will show up on the 3rd exam. Everything underneath it, if you have to move into 151, you are responsible for knowing all of those names and where they're coming from. Okay, yeah, awesome. Sawhorse. Yeah, where's the sawhorse? Turn that structure on its side. We got the fulcrum in the middle. Our lever on either end. There's your sawhorse. I didn't say it made sense, but that's where it's coming from. Okay? It's some random arbitrary person's perception of those shapes. So let's take a look at a couple fancy molecules here. CO2, we already did the Lewis structure for that. Let's look at the best one that we talked about. The best one we said was this, right? What is the shape of CO2? Okay. Follow our rules. How many groups of electrons around the center atom?
4.
Are there electrons on this face? 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 How many faces had electrons? How many groups of electrons are there? 2 groups of electrons. Nowhere in this analysis of groups of electrons did I say pair of electrons. I said groups. I don't care that that group, or the 2 groups of electrons I have twice as many electrons in them. I could put 50 billion electrons in that face. Let's just say I can. That's still one group. Okay? So 2 groups of electrons says the shape then becomes linear. Okay? Well, you know, we had all those other Lewis structures, so what about those? Because what should happen to the shape if I look at a different Lewis structure? It should stay the exact same because it's the same compound, right? Well, let's look at it. Are there electrons on that face? How about that face? How about that face? That face? How many groups of electrons? 2, which means linear, exact same result. Okay. Okay, well, I still don't believe you, Mike. Because I could have drawn my Lewis structure like this for CO2. Because Lewis said it didn't really matter where the oxygens were, we just put them around. That is a valid Lewis structure. But that looks bent. Does it not? Yeah, that sure looks bent. So why is that not bent? Because count your groups of electrons. You count the groups of electrons and there are 2, which means linear. So what does that tell us about our drawing? It sucks. Lewis structure does not represent shape. Lewis structure represents the bonds. If you want to make sure your Lewis structure now better reflects the shape, now that you've drawn it and gone, whoops, that looks horrible, Mike calls it sucky, I need to fix it to make it look linear. Cool. You've now better represented the structure to its three-dimensional characteristics. Have you changed any of your answers by doing that? No. You get the exact same answer. All it is it looks prettier. Does it matter? No. Exact same credit. All right. You want to look at one more?
One that's not linear.
One that's not linear. Hey, look at that. We look at carbonate, CO3 minus 2. So again, this is one that you should be able to draw, and you should notice that you will end up with 3 equivalent structures. We will draw only one of them. What is our electron geometry? We pick our center atom, and we ask, are there electrons? I appreciate the response without the question. Oh, now you stop. Okay. Oh, I didn't hear you. How many faces or how many groups of electrons? 3 groups of electrons. 3 groups means? Trigonal. Planar. Pyramidal is under 4 groups of electrons. We're under trigonal planar. Okay. Should I change that when I move to the molecular geometry? Are there any non-bonding pairs of electrons on that carbon? No. So does its geometry change? No. What is its molecular geometry? Trigonal planar. No different. You want another one? Or why not and a no? Wow. H2O. We draw out our Lewis structure, you'd end up something like this. And this would be probably what you would draw because you're like, hey, that looks pretty. I'm trying to make the symmetry and all that. How many groups of electrons around the oxygen? 4. Electrons, 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 electrons. 4 groups of electrons says the geometry is tetrahedral. This is our electron geometry. Somebody already shouted out, I think that might have been you, Sam, saying it was bent. Okay. What happens when we move to our molecular geometry? I now need to distinguish those 4 groups as bonding or non-bonding groups of electrons. How many bonding groups of electrons in water? 2. How many non-bonding groups? 2. If I follow that down in my pictures, in my tetrahedral shape, I will then shift across to trigonal pyramidal. This has how many bonding groups? 3. So that doesn't work. I move to the next one, and I have 2 bonding groups, 2 non-bonding groups, and I have the bent shape. The molecular geometry for water is bent based off of our Vesper models. Okay. All you're doing is qualifying in what happened. What does that mean happens with our Lewis structure? 2 fun answers on this one. You've gotten a sizable amount of answers. Nothing happens to our Lewis structure because the Lewis structure doesn't reflect shape. What if I want to change the Lewis structure so it better represents shape? I need to now just redraw water so that it looks more like the actual shape, and I would have a better representation of water. That's it. Okay. Looking at all of those images may be a bit tricky, so the other option you can do is you get a nice simple summary table. This is in the slides, you have access to it. It is also in the tutoring center. The tutoring center has added some extra pieces of information to it because 151 does the same type of thing. but they add more difficult concepts to it. So be careful using the one in the tutoring center because it's more complicated than what you need. So if we go through and read it, electron groups. For water, we had how many electron groups? 4, which means our electron geometry is tetrahedral. Next part, if I have bonding and non-bonding, I had 2 bonding, 2 non-bonding. What does that mean my molecular geometry is? Bent. This chart will set you up to come up with all the possible shapes that you can interpret for this class. Yes? Shape is not on this test. It'll be on the next one. Okay. Acknowledging how many groups of electrons, that's still perfectly relevant because we did that in Lewis structure. So this is kind of a refinement of identifying our groups of electrons. What was that? Lewis structure is on the test.
Dr. K is